Unit 10 deals with data and collecting it and analyzing it and looking at it and displaying it and things like that. Some of the stuff you've done in previous years, other stuff you new words to you. I'm not going to be making up a whole lot of new problems because it's a lot to do. So I'm kind of going through textbooks, examples, and definitions and things like that. So first thing here is the kinds of data they're going to ask you to be analyzing and working with. So first up, we have what's called categorical data or qualitative data. This is things like labels, not numbers as much. Numbers could be a category, that's possible. So with categorical data, doing things like adding it, finding the average, stuff like that, it doesn't make sense with the data you have. So that would be categorical or qualitative, whichever word you want to use. Then you have numerical data, also known as quantitative data. This is numbers that represent counts or measurements of things. People's height, the weight of the fish in your pond, uh, the length of your dog's tail compared to the neighbor's dog's tail, things like that. That's numerical data. Univariate data is a fancy way of saying one type of data. Bivariate is a fancy way of saying two types of data. So if your chart, let's say you're working with height and weight of people, that's bivariate because height is one and weight is a second. If you're just dealing with jersey numbers of a sports team, well, that's univariate because there's only one category, that's jersey numbers. So something like this. They'll ask you to tell whether the data is categorical or numerical and univariate or bivariate. So prices and ages of used cars at a dealership. Well, those are numbers you can work with because you could calculate like the car's age and the prices and stuff like that. So that's numerical data. And there's two of them, price and age. So that's bivariate. Jersey numbers for basketball team. Now this one, your first thought is probably going to be numerical. But it's one of those times when numbers are actually used as labels. So this has to be categorical because it doesn't make sense to use the numbers to do math. You're not going to find the average of the jersey numbers. You're not going to add them up or subtract them or divide them. You're just going to be listing them. So that's categorical. And there's only one type of data, and that's jersey numbers. So that's univariate. Length of songs played at a concert. So length would be numerical because that's a number. You can do operations. You can add songs together to figure out how long the concert was, so on and so forth. And it's only one kind of data, so that's univariate. And the last one there, zodiac signs and last names of students in your class. Well, you're not going to be doing math with last names or zodiac signs, so that's categorical. But there's two types, the signs and last names, so that's bivariate. And the next slide here, I included the answers in case you wanted to write them down. So you can pause that if you want to and write those down. All right, so try this one. You pause it and come back with the answers here. Same thing we just did. Tell whether it's categorical or numerical, and univariate or bivariate. So A would be numerical and bivariate. B would be categorical and univariate. C, categorical and bivariate. And D, numerical and univariate. And again, here's the answers on screen for you. Okay, so we're also talking about data displays and how to interpret them. And again, this is something you've done for years. This should not be new to you at all. So here you have a line graph talking about number of jobs in Florida by years there. So they're going to ask you which statements about the data in the display are true, and select all that apply. So we got to figure these things out. So A says the data are bivariate. So are we measuring two different things? Well, yes, there's years and number of jobs. So that is bivariate data. So A is true. B, the data is categorical. Well, no, because the jobs are numbers out of the years. And like you can average jobs and do operations with the numbers, so it's not categorical, so it cannot be B. Okay, C says the number of jobs nearly doubled from 2015 to 2019. So in 2015, it was right around 6,000, but in 2019, it's around 12,000. That's around double. So C is true. And D, the number of jobs increased by about 3,000 from the same time frame. Well, if it was at 6,000, then went to 12,000, that's not an increase of 3,000. So A and C are your answers. All right, same idea, circle graph. Again, you've seen this before. This should not be anything new to you. Let's go ahead and try to answer these questions real quick. Figure out which one of these statements are true, then come back to the answer. So the data are numerical. Actually, they're not. They're categorical. Because yes, it's years, like ages, but they're being done as labels. And you're not going to sit here and like average the years and ages and stuff like that. It's not going to happen. So A is out. B, the data are univariate. Well, we've got student ages, and yeah, we have student ages. That's it. So B is true. Okay, C, number of 16-year-old is double the number of 18-year-olds. See, 16 has 17 people. 18 has 7 people. So that's a little more than double. So, no, it's not double the number. It's a little more than double. And then it says there are 3 more 15-year-olds than 17-year-olds. So there are 14 people who are 15. There are 11 people who are 17. And that gives you 3 more participants. So, B and D. All right. So we're not going to have examples of every single one of these things because, again, you should have done this before. So this is a way to choose and create appropriate data displays. And choosing it can depend upon the kind of data, categorical, numerical, univariate, bivariate. So these are your suggestions. When you have univariate categorical data, a bar graph or circle graph is your best way to display it. It's like bar graphs use it in categories, and circle graph is the parts of a whole, like we just had. When you have univariate numerical data, a histogram, a stem and leaf plot, a box and whisker plot, a dot plot, all of those things are good choices. When you have bivariate numerical data, a line graph or scatter plot is usually your best choice. So here it says we're going to analyze the data and create a display that appropriately represents the data. Explain your reasoning. This is stuff you did in elementary school. You're making these graphs. So go ahead and make your graphs real quick and come back to the video and get the answers and see how close you came. All right, so the first one, a line graph is your best choice because you're comparing things over time. So it looks like that. There you see it in the screen. The second one, a bar graph is one way to do it because you're having these categories here. So you got fruit, and you have number of students, and you have the bars for each one. All right, misleading graphs and data. This is a major skill to have in life, quite honestly. Data displays can be misleading. And what that means, they say it's a graph that is not drawn appropriately. And that's a way to phrase it. Um, Misleading is kind of like saying it's lying to you. Like maybe the data is true, but the way they're presenting it is false. And this can make people misunderstand the data. For an example, if you look at election maps after every single presidential election, you'll see blue states and red states. And both sides will argue about what it means. A lot of times the red states will go, look at this, we have so many more red states than blue states. But when you think about it, out in the Midwest, you got a whole bunch of open land and mountains that don't vote. When you actually find a map that shows you the colors by county in each state, it's a lot closer than what the giant map shows. Is the data true that state's votes went to that candidate? Yes. But within that state, did every person vote for them? No, of course not. So when you're looking at the graph, you want to think about certain things like, is it labeled correctly? Is the scale evenly spaced out? Does it begin at 0? If not, is there a break on the graph indicated? Does the graph need a key to explain it? Is everything labeled correctly? The axes, the sections, so on and so forth. And is everything the same size? Like, are your bars the same size? Or are some drawn wider to look like better or whatever? These are all things people do to make a graph mislead others. So for example, like these two here. So A has an academic school year, cost in dollars, and says tuition, room, and board at all colleges in the state. Which, looking at is like, wow, that's a huge increase every year, right? It's a steady, large increase. That's the picture shows you. But look at your axes there. You're starting at 19,500, not 0. So your first bar is actually at almost 21,000, not quite, probably about 20,750. Your second bar is at like 21,250. That's not even $500 difference, I mean, roughly speaking. And it looks like each time it's about the same thing, between $500 and $700 difference. Like your last bar is at 22,500. The first bar is already over, is almost 1,000. That's only like $1,500 difference. Now, is that a lot more money? Yes, it is. We're talking about $20,000, $22,000, $23,000. $1,500 is like not that big of a change. But the graph makes it look like it's a huge change. It's not. So what they did was they did not put a 0. There was no break in the graph. They made it look like the graph was this huge change every year when it's really not that much of a change. All right, right hand side. So what do we have here? So we've got your wages, your year, how much you're getting paid working at a fast food restaurant, cool beans. So let's look at your scale first. Starts at 0. That's good. There's a break. Okay, cool. That's fine. That indicates that there's a jump. But the numbers are all different. It goes up by 2 cents, 2 cents, 2 cents, 2 cents, 2 cents, 1 cent, 1 cent, 1 cent, 1 cent. So again, it looks like there's a huge jump from here to here, right? Oh, huge jump in money. Look at the numbers. 9 and 9.04. 4 cents, in my opinion, is not a big jump in pay. I could be wrong, but that's just how I see it. And again, here's their explanations. All right, same idea again. You do it on your own. Figure out, if you can, how each graph is misleading. And explain why it might be misinterpreted. So pause, come back. All right, so in A, you look at your scale there. The scale goes from 0 to 50, okay. Then it goes up by 100, then up by 100, then up by 100. So it has a small jump first, and then a much bigger jump, and it stays that way consistently. So people might assume that student D sold a lot more tickets than everybody else, which they did sell the most, and the numbers look like, oh well, E had a lot more than B, C had a lot more than B, but look at it, it's 100 tickets more, or like 25 tickets more. Is it a gap? Yes. Is it as big of a gap as the graph implies? No. So right hand side shows your ages. And if you look at the scale, first of all, it goes 0, 5, 10, 15, 20, 25. That's cool. But look at the lines, little blue lines there. Like this spacing and this spacing, pretty even. That spacing, pretty even. Huge gap here. Like that's what, two, almost three of those right there. And then back to small gap again. So they put a huge gap right here to stretch the bar out even further and make it seem like it's a much, much larger amount than it really truly is. Like you might assume, oh, well, between this age range and that age range is a huge jump. Now look at that graph. But look at the numbers. This is about what, 12? That's 5. That's a difference of 7 people. Not that drastic.